It's officially 2 o'clock and I see a lot of people joining us. So big welcome to everyone. We're not getting started just yet. We're gonna wait a few more minutes for more people to be able to join. But you see there on the screen that we have a question for you. So you can join from your computer in menti.com and write this 8-digit code to be able to input your keywords, or you can do it from your phone by scanning the QR code. And we're going to wait a few more minutes because we have people joining us, but feel free to share. Use your creativity to tell us what do you think these pictures have in common. Okay, welcome to those joining us now. Feel free to join our Menti on the screen. Let's wait one more minute before officially kicking off. And in the meantime, please add your words to the Menti. And I hope this is working. If you see that, I will try myself here to see. Yeah, okay, it seems to be working. So let's see what you have for us. And yeah, I think we can officially start. But I see that some people are still joining and putting your words in the Menti. They are hidden for now, so you don't get biased. But there are some words that are already, popular because they appear bigger on the screen. So let's wait a little bit more because I see there are around 30 people who are joining the Menti. So we give you a few more moments to say, what do you think all these pictures have in common? And the speakers of today should not cheat, huh? Okay. We have a lot of words. I think it's time to do the reveal, if I can.
Oh,
okay. Interesting.
Yeah.
Now, if you see other ones that you want to endorse, it's your moment. So we have a big geology in the middle. It says a lot about our audience today, I guess. Okay. Just think we are ready to start then. So thank you very much for adding your words there in our Menti. We will come back to this afterwards. But if I can move forward, okay, great. So good afternoon, everyone, and thank you very much for being here with us today. I'm Renata Barros from Geosurveys, and I will be your host for this webinar. And today we will have a series of short presentations back to back, and then we'll have a Q&A session in the end. So please use this Q&A function that you see there on Teams to add your questions at any moment, and then we will come back to them after the presentations are done. And also, we are recording this session, and we will make it available on our YouTube channel afterwards. So, sorry. Right, so without further ado, it's my pleasure to introduce the part of the GSEU project that brings everything else together, the geological framework setup. But before diving into this, just a quick word about who we are. So GSEU, the Geological Service for Europe project, is a collaboration between 49 partners from all across the continent, and with the vision to build a permanent network to provide geological data and information and knowledge for Europe's subsurface management. And this is really key to manage our resources and opportunities linked to the subsurface in a sustainable way and to achieve climate goals. So the part of the project we're exploring today, the geological framework setup, is one of the thematic areas that we're working on, that you see there on the left-hand side. And the goal is really to develop harmonized data, information, service for each of those, and then make it publicly available through EGDI, so the European Geological Data Infrastructure, and to keep an open channel of communication with our stakeholders. So it is the case for all of these thematic areas that they don't stand alone. And in the case of the geological framework setup, it's really strengthened by the geological mapping and modeling expert group of Eurogeosurveys. And also, of course, by decades and decades of national expertise all across Europe. So it's important to know that what you see today is beyond GSEU. It's really the result of this long international effort to help Europe have this one big picture about its geology. And right, so to do this, you will be informed and hopefully entertained by some of the top experts in the topic in Europe. Please exclude myself, but they are joining us from all over the continent, which is pretty cool. So we will start with the map moment with Hans-Georg speaking from Vienna and Urszula from Warsaw. Then we will follow with the hammer moment with Kristine presenting from Hanover. And afterwards, Cecile will present the anthropogenic moment all the way from Orléans. And last but not least, also presenting from Orléans, Philippe will do the 3D evolution moment. And of course, myself here in Brussels, I have the most difficult task of trying to pass their slides at the right time. So bear with me. Let's try to do this together. And we do have some very cool slides and very good presentations today, because yes, Europe has a wealth of geological knowledge, but there are some open questions. Is this knowledge enough to achieve these goals that we were talking about, big ambitious climate goals and so on? And is the real challenge accessing this knowledge, or is it understanding the gaps that still exist? And when data is missing, does it really make a difference in my life? Hans-Georg, are you ready to start answering that?
Yes, thanks, Renata. I'm ready to start our story. Let's begin with a fictional geological block diagram, in this case in the vicinity of a city by the sea. The diagram shows numerous forms of human use of the Earth's surface and subsurface, some of which are in close proximity to each other or even intertwined. Surface infrastructure, for example, requires stable building ground. Planning measures in forestry and agriculture depend on reliable information about the shallow subsurface. Our living environment must be protected from natural hazards such as landslides, the use of geothermal potential, mineral extraction in mines, groundwater management, or the construction of underground infrastructure like railway tunnels. All of these require a precise understanding of the medium to deep underground of the geological subsurface. This also applies to marine areas, for example, when it comes to securely anchoring offshore wind turbines to the seabed. And last but not least, we want to protect our geological heritage. In this example, beautiful earth pyramids as a non-material value in itself, but also for the development of geotourism. The intensive use of geological resources in this example is possible because there is a precise knowledge of the geological conditions. This is what types of rocks we are dealing with, their spatial relationship, the position of fractures, the position of the groundwater table, the fresh saltwater boundary, and so on. In this example, everything is apparently well known, but yes, with the fictitious block diagram, that's not really surprising because it is designed to illustrate an ideal case. But how does it work in practice when we need geological information for an applied project somewhere in Europe? Let's take a fictitious example once again. An underground hydrogen pipeline from Lithuania to northern Italy, co-funded by the European Union in support of the energy transition. In order to do the planning, we need good information on the subsurface because we have to dig a 2.5 meter deep trench all along that way. And digging in sand or gravel is obviously much cheaper than, for example, in granite or other hard rocks. Well, at that point, the International Geological Map of Europe at the scale of 1 to 5 million immediately comes to my mind. This map gives me, as a planner, a great overview of what I might expect in terms of geology, right? Well, that may be true for a very, very rough planning, but quite soon I will need much more detailed geological information. The question is, how? I guess Urszula can help with this. She will now tell you more on the mentioned map of Europe and give advice on how to find, hopefully more detailed, other geological maps. Urszula, can you take over, please?
Yes, the International Geological Map of Europe at 5 million scale is the excellent resource for examining geology of Europe as a whole. When we're planning infrastructure, the geographical location is the first thing we consider. But the next step is looking at the geology. Geology is not limited by administrative borders and also exists beneath the surfaces of ocean and sea. So even we cannot see that. IGM 5000, this is the short name of International Geological Map of Europe at 5 million scale, is a great example of fully harmonized geological maps. What does it mean? It means that it has a common vocabulary used to describe the geological units, and also the fully harmonized geometry of the geological units. Next, please. To explore geological map of Europe, you don't need the specialized GIS tool. You can use also the EGDI web viewer, map viewer, yes, and it allowed you to view data, and also clicking of the specific object, you can find more information about geological unit. You can find information about the lithology. It means type of rock, the age, origin, regional names also, if any. It's also possible to obtain information about the data itself. There is a special button that takes you to the metadata catalog. Next, please. Searching the EGDI metadata catalog is like searching for publications in library catalog. You can use filter to narrow your search. For example, if you want to find the geological map of specific country. The results is a list of metadata records, and you can click on the specific record and go to more detailed information. You can find information about the full title, abstract, also about the publication dates, spatial extent, and licenses, and also about the links to existing web services, just to use the data and explore them. What's more, EGDI metadata catalog doesn't just store only the own metadata. It also connects to the catalogs of individual geological surveys and collect automatically metadata according to the predefined rules. That's why you can find information about many different maps and sources. The IGME 5000 is not detailed enough, as it was mentioned by Hans Georg, for investment planning. That's why so important is for the GSEU project to inventory geological maps in all European countries. Not only is information about the scale of the study important, but also current coverage of the country with data at the given scale, as well as information on whether the data is vector or analog, if they are harmonized or not. We collecting also the information about additional attributes that describe the geology presented on the maps. For example, information about age, lithology, genesis, tectonics. We have to say that geological maps are the starting point for all further detailed research. Example, exploration for deposits. So, why do we need more detailed data, geological data, for planning pipeline location? When we are planning investment like pipelines, we need to know exactly what the ground is like. This is because it affects how we build the infrastructure and how we will maintain it afterwards. Furthermore, if the investment is located in a place where there are mineral deposits, this will prevent the subsequent exploitation. All these things have financial and ecological consequences. Inventorying geological maps will help to identify gaps in geological mapping data. A lot of work is still needed to provide detailed and harmonized data for the whole of Europe. The inventory will help assess the gaps, but will also make existing resources findable and accessible. Next, please. So let us take on the challenge. Fill the gaps and harmonize existing data. Kristine, could you explain how this could be done?
Dear Urszula, I will do that with pleasure. Can we have the next slide, please? Well, in the next couple of minutes, I'm going to tell you how geological maps are being created and what we are doing in order to facilitate that across the whole of Europe. And I can tell you this is not only by the use of a hammer. May I have the next slide, please? First, you can see the rock unit is being recognized in the field, also with a hammer, but not only. You take samples, it's sketched, noted, and the samples that have been taken, often by the hammer we have been seeing here, is being used then in the laboratory, in order to find out more about the rocks. Here we can, for example, use a geochemical analysis, as you can see in the third slide, but also the thin sections of rocks where you can very nicely recognize the minerals a rock is being consisted of. The results of this thorough scrutiny is being used in order to compose a complex geological map, often in several layers, and developing geological models of the subsurface. And I can tell you in this context that also 3D models are very much connected to our 2D geological maps, because the geological map is a model in itself. May I have the next slide, please? Well, you may know that if there are 10 geologists as here looking at an outcrop or at the rocks, there are at least 20 points of view. We ask ourselves, what shall we call it? Next, please. Different geologists with different background information, different background education have also different approaches to describe and interpret the rock and the rock type they are observing. You have, for example, a mineral resources expert who will see in this outcrop sand and clay and silt. You will have a database specialist who only recognizes, oh, this could be ID 741142. We have a magmatic geology expert who thinks, this is only the dirt laying on the top of something interesting. And you have a quaternary geology expert who might think, oh, this is a glacial sediment, we have a diamect here, and many more. And this is not only the case between individual geologists, may I have the next slide, please, but also internationally between geologists coming from different countries or from different regions. Europe has many regions and many countries, and what we can see here and recognize here very graphically, that different countries have developed different nomenclatures over the last centuries in order to describe their geology. This concerns the rock types as well, as Urszula described earlier, but also the age of the rocks, the stratigraphy, the genesis, how it was generated, and other characteristics of rocks. But geology does not know political boundaries. So we need a common language, a common denominator to make our mapping results understandable for our neighbors across our political boundaries and understand what they have done and what they have mapped. May I have the next slide, please? Thus, we are creating a common denominator, a sort of geology Esperanto. These are common vocabularies, dictionaries for the entire Europe, perhaps also beyond, to describe what kind of rock we have in the same way, in the same term, and with the same description. But what you can see here is our tree diagram of our rock types. Between each of these little blue bubbles, you can see not only the term of the rocks, what is it? A granite, a limestone, a sandstone, a diamect, what we saw earlier, but also its definition, its references, and the relations between the terms. We have now already, I think, 349 terms, and these are growing. Can I have the next slide, please? So, why do we need to understand the geology across our boundaries? Also, Urszula said a little bit about this. It is important for knowing the ground beneath our feet, because we need to build infrastructures, for example, bridges or railway lines across political boundaries. Remember, geology does not know political boundaries. For mitigating geological hazards, for finding mineral resources, finding groundwater, to find secure building ground for our houses, to find material to heat our houses, to find material to build our computers with. Geology is almost everywhere in our lives, and it's even there to create art. We need a special type of rock, for example, marble, as we can see here. By the way, this is a famous Carrara marble. Can I have the next slide, please? It's not only important to describe our natural rock skies, rock which we find in nature and which was built by nature, but it's also important to describe the human-made deposits, because they are increasing in the numbers in the last, well, decades, I would almost say a century, and it's important to map those as well. So we are also developing special vocabularies to describe these human-made, these anthropogenic deposits. And my colleague Cecile Guern from BRGM is going to describe this now. Cecile, please.
Thanks, Kristine, for introducing the questions of anthropogenic deposits. So let me tell you more about these deposits first. So actually, human activities enormously impact the soil and subsurface. Reworked soils, sediments, and many materials created by humans are found almost everywhere. These are called human-made, as you said, or anthropogenic deposits. And we live on these deposits and face them during building or redevelopment. Sometimes we expect them, sometimes not. For example, as shown on the left photo, a common finding when building new houses in big cities or even in small villages is the presence of former waste disposal. Everybody forgot about it, but it may lead to bad environmental surprises, as you can imagine. On the other hand, as shown on the right photo, we can also create nice parks on the top of former landfill deposits if we take the right precautions. Next. And so many human-made deposits are made on waste disposal, on waste materials. We've just seen the examples of municipal waste. But construction and demolition waste are also frequent. They represent large volumes in the cities that showed large destruction during the World War II. And this series of photos shows one hill made of World War II demolition waste in Berlin, in Germany. It's up to 40 meters high. As you can see on the right photo, constructions were made on the top of the hill, and a big forest grew on it. It's now considered as a protected area, although the groundwater below is degraded due to the infiltration of rainwater through the deposit. And industrial waste has been used in some places as well. The brown layer in the photos here shows an example of such material used in human-made deposits. But other materials than waste are also used, fortunately. In the photos here, the yellow fine layers correspond to dredged sediments from the Loire River in Nantes, France. They were used to rise and flatten topography. The next, please. Oh no, just I also wanted to say that natural materials, so maybe you can move to the previous one, are also used, especially in road and railroad constructions. And on the left photo, on the top of the layer, you see some technical material used for road and street construction. And now let's move to this photo, so meaning that the human-made deposits change the landscape by rising, filling, or even creating new land. And this photo especially shows an example of artificial island that was recently created with human-made deposits in the port of Rotterdam in the Netherlands. And so another example of deposit is mining residues that compose some human-made deposits. And the two photos to the left show several examples of mine tailings in France. And as we can see, they really changed the landscape. But also development activities like the preparation of foundation for built infrastructure or the digging of tunnels, they generate large amount or large volumes of excavated soils and materials. And some of them are used for landscaping, for instance, to create some hilly parks in the cities. And the photo top right photo shows some use of excavated soil materials for landscaping in France. And the fourth photo that on the top, just the last photo on this slide, shows an example of industrial processing tailings in Germany, which also impact the landscape. And now let's move to to this example of maps and 3D geomodels. So we've seen that lots of types of human-made deposits, of material used in human-made deposits. But actually, as shown on these two images, when these anthropogenic deposits are represented, only a gray area is visible, with no information on their content and properties. But due to their heterogeneity and sometimes non-natural nature, their stability and properties are difficult to predict. For example, for rainwater infiltration or regarding the presence of contamination. That is why it is important to map and describe them better. But actually, no complete harmonized and coherent vocabulary to describe this deposit exists across Europe. Next. And that's why we're creating this vocabulary, to improve the relevance of our maps and 3D models. But we do not reinvent the wheel and use existing vocabulary as much as possible. For instance, the human-made materials list is adapted from material science, as shown on the right of this slide. And the natural material are described by using geological terms, as shown on the left of the slide. And we also introduce some additional descriptive aspects in the middle of the slide, like origin of the material, purpose and process of the deposit, to facilitate the use of geological maps and models in spatial planning and design processes. And in this slide, we show an example of what we can achieve with a more precise description of the human-made deposit. The top left image shows the initial geological map of the city center of Nantes, France. And as you can see, the presence of human-made deposit is indicated in the strict zones. The images on the right of the slide show detailed maps of the human-made deposits located in the red rectangle of the first image. As you can see, the type of deposit changes with depth. In this example, the red deposits have a higher intrinsic pollution potential than the other ones. Actually, this is linked to the presence of some industrial residues, as we saw in one of the photos earlier. And the yellow deposit corresponds to the clean dredge sediments that we also saw in the photo earlier. And what is important is that with this common vocabulary in hand, we can improve the maps and better assess the risk and use the opportunities that are associated with the subsurface of our built environment. They allow us to improve the 3D geomodels, as shown by the bottom image. But by the way, how do we build such 3D geomodels? Philippe, can you tell us more about it?
Yes, thank you, Cecile. Yeah, I have some images, some moving images here to describe 3D geomodeling, and what I'm going to show to you is taken from actual studies. So let's keep talking about anthropic matters and back to the former mines, and especially to abandoned galleries that over the time may collapse and cause the subsidence of the ground and possibly damage buildings. For that reason, and to prevent such event, we need to have underground mapping. So geological map is a model. It is displayed in 2 dimensions on the topography. And there is a very natural continuum between geological maps and 3D geological models, simply because they represent the same geology. We talk about 3D mapping, where any 3D point, X, Y, Z, is associated to geology, exactly as on the geological map in 2 dimensions. So you have seen previously that in the field on the outcrop, we can identify the rocks, and we can also measure the depths of the geological contacts. The way they plunge in the ground is a precious information to constrain and to model geology at depth. And this is what has been done in this study dedicated to a seismic event that occurred at the junction of a triplet of faults. These faults have been modeled using the depths measured in the field, so exactly as we have seen. And the question was to estimate if the heavy rainfall episode that occurred in the months before the event may be responsible for it. So to do that, we meshed the surfaces of the faults that were modeled to simulate water circulation, water flow in the underground, and especially we simulate the pressure in that area. You can see the result here of this simulation, and at the location of the seismic event, an overpressure of 10 bars was simulated. So such an amount make the heavy episode of rainfall a good candidate to explain this seismic event. But nevertheless, the only way to really access the underground, the only straightforward way is to drill. Doing that, we can access directly to the rocks, so we can identify them, and we can also measure the depths in these rocks. It's a kind of underground outcrop. These kind of boreholes have been used in this new study dedicated to water resources. Hundreds of them have been used to set up this hydrogeological model in 3 dimensions. As you can see, it covers a surface of several 10,000 kilometers squares down to a couple of kilometers at depth. By the interpretation of the boreholes, we were able to model geology in terms of aquifer and impermeable formations. And then knowing the direction of water and measuring the permeability of the rocks in labs, we are able to simulate the flow of water and to calculate the theoretical amount of water that can be pumped in that area. On top of that, if we add the incoming rainfall, we can, and this is what the local authority do, manage their water resources. So we have seen direct way to have information on the underground, but there are also via geophysics, for instance, the seismic profile you can see here, or airborne surveys, give access also to the underground. And this is this kind of method that are used often in geothermal energy. Here, it is crucial to reach the relevant resource at depth. And fluid flow rate and temperature are the two main drivers to determine the resource. Here, a geological model is used to foresee these reservoirs that are used in geothermal energy, and then that can be, for instance, driven by a fault, as you can see here on this animation. But on top of that, the geological model, or maybe more precisely, the geometry of the geological model, is also used to simulate temperatures of these resources. So we can, doing that, have such a map you can see here in the screen representing temperature at the reservoir. So we have some data, as we have seen, but only at some places. This is why we need methods to compute them to obtain a broad model of geology in 3 dimensions, for instance, using geostatistics. So these methods are implemented in a code, and if we add to this code user interface, I think the video is frozen on my screen. Yeah, okay. If we add user interface, as you can see here on the screen, we obtain the kind of tools that are used to construct our geomodels. 3D mapping, because we talk about 3D mapping, is also very useful for mineral resources. In this kind of projects, about all the data we have seen, the kind of data we have seen so far are used. And here, the main challenge is to estimate the amount of mineral that can be extracted. So to do that, I think you know that now we do this 3D mapping. So we use the data we already have seen, like drill holes, like seismic profiles, direct measurement in the field, for instance. But we focus on a single formation that is hosting the mineral we want to extract. So we construct the representation of this formation, and knowing the volumes, we can calculate by the concentration of minerals the amount that can be extracted. So altogether in this video, we have seen how much the knowledge of geology at depth is important for applications. This is why in the GSEU projects, partners are sharing best practices and gathering a toolbox based on open source code to strengthen our capabilities in 3D mapping. So thank you for watching and listening. We really hope that our presentation shed some light on the question that was posed in the Menti at the very beginning of this webinar. We really hope so. What do you think, Renata?
Thanks, Philippe. I'm sorry for a little problem here, so I will leave this hanging while I try to reopen the presentation, but I asked for everyone there in the audience because I haven't seen anything coming up in the Q&A. So this was the last presentation. You have a little moment now to add the questions that you may have while I try to make my PowerPoint come back to life. And we come back full circle to the beginning of the session. But if anyone didn't believe me when I said that the geological framework setup is bringing everything together, I hope now that you believe me and that they were able to demonstrate this for you. So bear with me just a little moment as I restart things here. And I'm sorry about that. And let's see if some questions come up in the meantime. So it should be working now. Okay. It just doesn't like to do two things at once. I can understand. Okay. So thank you for your patience. And now this should be working. So we had a very generic geology as the connection you've seen between the pictures, but after hearing from the geological framework setup team, do you see any new connections, maybe? Something a little bit more specific? We all agree geology, of course, and we're happy you brought this up. But this is a different Menti, so it's not the same code as before. So you can join on the computer, on the browser with this not for 8-digit code, or by scanning the QR code once again. So let's give you some moments, see if this is working now. Once again, they are hidden. So let's wait a little while. To see what's maybe something new comes up. Okay. It's being a bit slow here, but I see that some things are coming up. Don't be shy. You can enter the Menti with the QR codes that's still there on the bottom left. So let's see, we have a few brave people who have put their answers. And if I can show them now. Ah, I like that. Not so much agreement anymore, but this is a good thing. But yeah, we hope that you could see a little bit of the key aspect of everything we talk about in terms of resources, of opportunities, of subsurface management. It really starts with these different moments that they prepared for you here. So that's a nice thing. Let's see if this would work. If I can compare them. So this was the one of before, and now it's a little bit more varied, which is nice.
Right.
So cool. Thank you very much for those joining the Menti. I think we're happy with these results. And my PowerPoint is not happy, but now, as promised, this Q&A time. We have some bit more than 10 minutes there for Q&A, so I will stop sharing. And let me see what we have there. So we have a few questions. In case you've put a question, but you would prefer to say it out loud, we can try this. I don't promise anything because this setup is a little bit new for us all. But if you're happy with it, I will just read your question. And if you want to add anything, try to raise your hand so I can find you and see if you can talk to us. So a first question from Harvey. How shall we build a global repository for optimally queryable, that's a difficult one, so possible to query, geological mapping? Who would like to start with this one? So a global repository and something we can query. Any thoughts?
Well, I would say that you already talked about it at the beginning. I think, Renata, it's the goal for the GDI platform, in a way, to have this kind of information, not maybe at a global scale, not for all the world, but at least for Europe. Yeah.
And
Yeah, I don't know if he meant global as in really global, which I
Yes.
think is a huge challenge. But it is true that in European scale,
Mm.
it is pretty much the work that you are doing now. And we have another question from Dina. What are the next challenges for the European Geological Surveys? And we have 4 different ones represented here, so don't know if you would like to quickly, in this context, of course, and in the GSEU project wrap up towards the end of the project in a couple of years. What are the next challenges? Who wants to start?
Sorry, Hans-Georg, please.
All of us could answer, of course, but in this very case, Renata, I think you sit at the best place in the office of Eurogeo Surveys and working in the strategic work packages yourself. So maybe in this case you could give the answer.
Okay, they threw it back at me. No, but of course, I think I would say one of the main next challenges is to really make all of this work to be part of a permanent structure, because a project's duration is limited, of course. So we're really working now to make sure this is durable. I hope you agree with this.
Yeah, for sure.
Let's
Maybe I can add something on that. I think that the challenge is ongoing, I would say, and what we are going in terms of standardization, common practice, and so on at the European level will be very helpful to work really more efficiently together, in fact. And then we can envisage stuff that that is not really possible for now, but will be in the future, like, of course, 3D mapping of Europe, this kind of thing. But to do that, we need to share a common framework and a common structure. So this is on what we are working, and I think it's very important to this federation at the European scale.
And
Yeah,
another
absolutely.
challenge that we are facing and that is coming up is, of course, also to deal with the new methods that are coming up. For example, you have surely heard and are aware of the discussion of artificial intelligence in geological mapping and modeling. This will be certainly one of those challenges and also interesting tools how to use it that are come up and that we will deal with.
That is true. Challenges and opportunities alike, I guess. And
Absolutely.
I see we have a raised hand. I will come to you, but first I wanted to ask a question for Cecile that has 2 endorsements, so I think this will be good for a few people. So when does the nomenclature for anthropogenic deposits become available for application?
So actually we're ending the building of the vocabulary itself. So we're finished with the human-made materials, but we are still working on the other attributes and wish to test the vocabulary in 2026. And so our deadline to make the vocabulary available is 2027. So at least, yeah, I would say within 2 years, it should be available now. Have to be a little bit patient, I would say.
And linked to this is another question on how much time you think it will take to finish a comprehensive vocabulary for anthropogenic deposits, okay, but for lithology. And it's more for Kristine, I think.
Yes, absolutely. Well, we have time to build our comprehensive vocabulary within the GSEU project until the end of 2026. And I think until then we will have some considerable vocabulary to build and also to present to you all. Of course, it depends on how comprehensive is comprehensive. If we are going into very much detail. This will surely take a longer time. At the moment, we are more working on scales, and I have seen a question also in the chat by Matthias Steinbeckel on what is the next preferable scale.
That was the next one. Please take it.
Yeah, this is also a question that can be answered by Hans-Georg, but the more detailed we get with our vocabulary, of course, the more terms need to be agreed, and the more time we need to do this. But at the scale we are working at the moment, this is between 1 to 250 and 1 to 1 million, perhaps even a little more detailed. This will be until end of next year. And Hans-Georg, I don't want to take away that question to you. What would be the next preferable scale? I think I'm sure.
I can add up here. Yeah. In our strategic paper for the Commission on how to proceed with the geological service of Europe, yeah, we were also requested by the Commission to let them know a detailed list of products which they could expect from this kind of institution. Yeah, and what we wrote down there is a basement map of Europe, so without quaternary deposits at the scale of 1 to 1 million. Yeah. And if you remember, that was already attempted in the one Geology Europe project, but not finished. The result is not complete and not harmonized. But that could be the next step. And our survey, which is done in the metadata task, which Urszula explained, we observed that the relative best complete level of completeness of maps over Europe in more detail is 100,000, 1 to 200,000. But this is not possible to do it in one project for whole of Europe. But what I expect is that at this level of detail, regional maps and according projects will take place between 2 or 3 countries, but based on a homogeneous data model and the vocabularies we developed now. Yeah? And these maps and regions can grow together over a long time span of, I don't know, 10, 15, 20 years. That would be my expectations regarding scale.
Thank you. I wanted to get one last question from the Q&A before giving the floor to our raised hand. How do you deal with the problem that geology is not homogeneous across countries and also partly within countries? The geology knows no political borders.
What a question. Well, if I may start, well, Stepien doesn't mean that the geology is homogeneous, but the description of the geology. And I think within this project and in the projects that has been working before on this, one was One Geology Europe, which was mentioned. The other one is the Inspire Directive, and there's also for the marine region, the EMOTNet project. There are many initiatives who are working on harmonizing the geology across our political boundaries. And the answer is cooperation, communication, working together and setting up projects for this, to work on the inhomogeneous descriptions within the countries itself. It's actually the same answer. It's the initiatives in each country. I know that in Germany, for example, we are working on a general legend for these large-scale geological maps in Germany, the UGL, in order to harmonize also the descriptions for all our 16 states within Germany. And I assume that this is also happening within other countries. I know, for example, that the BRGM has a very nice harmonized map. pink geological mapping database, I think it's a scale 1 to 50,000. So this would be my answer, but Hans-Georg, Philippe, Urszula, Cecile, I'm sure you have more answers on that one.
Maybe just a few words, and it makes me thinking about that. Is that and I understand the question the same way than you, as you, Kristine. That it's more about the interpretation and how we see geology, not the geology itself that has no border, as you said. And I think it's very important to not to mix the observation and the interpretation. And historically, it was done all the same, because when you observe a rock, it has some characteristics and so on. And these are facts. These are really observation. And then you can name this rock with the name that correspond to a model you have in mind, or to correspond to what is the level of knowledge about geology and so on. But that can be changed in a few years because we have new theory or whatever. So it's important to not to mix the observation and the interpretation, and this really help to solve this kind of questions.
Thank you. I am afraid we are really running out of time, and I wanted to try to give the word to Julia. So we have plenty to discuss, I know, but keep an eye on our next initiatives, because we will for sure have more discussions about this. So, Julia, I think you can unmute yourself now. Hopefully this works.
Thank you very much. Hi. For the insightful presentation. And it's like the last question. What are you optimistic about the AI revolution in European geology? Probably, maybe you believe we'll have some kind of digital twin one day for European geological map. And thank you for your time and for the presentation. It was great.
Thanks, Julia. Very last answer for this tough question. Who wants to go?
Did I understand you right, Julia, that it was about artificial intelligence, AI?
Yes, and why we are optimistic that it will help to develop the geology of Europe
how
in the future.
AI will help geological future, our geological future, yeah.
I think Cecile had something to say.
Yeah. So there are plenty of ways that AI can help us, but first, for data mining, it's really important to help accelerating the gathering and treatment of data. This could be really helpful, all the more as we have an homogeneous way of describing the data. So this can really speed up and help us treating more data than we are able to do now.
It can also help us to find data that are hidden somewhere in hidden resources, and it also can help us with maybe only semi-artificial, half-human intelligence to generalize our geological maps, which is one of a big task if we are coming from large scales to small scales.
Right. I'm very sorry, but we will have to end now. Thank you very much to those who could stay with us a few more minutes. And thanks to the 5 of you for your great presentations. And we can watch it again on YouTube afterwards for remembering some insights. Thanks a lot, and hope to see you in the next webinar.
Thanks
Thank you
Renata,
for everyone for
attending.
moderation.
Thank you.
Thank you.
Thank you. Bye-bye.
Thanks. Goodbye.